Assalamualaikum warahmatullahi wabarakatuh. My name is Anjas Wibisana and I want to present this paper entitled Car Converter using FLC to manage power consumption from PV directly on this conference, namely International Conference on Applied Science and Technology. The authors of this paper are Indana Sudiarto, Farid Dwi Murtianto, Anang Putikarso, and me, Anjas Wibisana from Politeknik Elektronika Negeri Surabaya. This introduction is to explain that this paper was made. For a long time, petroleum was the main source of energy. Because the impact is very bad for the environment, petroleum was replaced with renewable energy. One of them is solar energy. To take advantage of it, use solar panels to convert solar energy into DC electricity. The output power generated by PV depends on the intensity of the sun and the temperature of solar panel. Thus, PV output power becomes unstable. To overcome this problem, a converter is needed as a power stabilizer. Car converter is one converter that can be used as a power stabilizer from the PV output. In this research, FLC or fuzzy logic controller is used as a control to stabilize the output voltage of car converter. Now, let's move to the next slide. This slide is to explain modeling system. From the block diagram system, it can be known that PV is the main energy source used to supply car converter so that the output voltage can be stabilized for DC loads. To stabilize the output voltage of car converter, a control is needed so that FLC or fuzzy logic controller is used as the control. This is the system simulation. From that picture, this simulation used 12 PVs where the configuration is 4 series and 3 parallel. Thus, the output voltage generated by the PV is 70 volt. In this CAC simulation, there are several setting points used, namely 400 watts, 600 watt, and 800 watt. The system simulated using PowerSim software, and after being simulated, it can be seen the response form of the system when using control or not, so that the response can be compared. This is PV specification table used in the system simulation with a Pmax of 100 watt for each PV. This is modeling of CAC converter. This slide contains a formula for finding the value of the duty cycle in electronic components such as capacitor and inductor for CAC converters and the results of calculation used to design the CAC converter. This is modeling fuzzy logic controller. This is rule-based FLC that we use with following criteria. If output power converter is not reference set point and far from set point value, the duty cycle must be large so that the output power can reach the set point rapidly. If output power converter is less than set point, then the duty cycle must increase to reach set point power. And the last one, if output power converter value is greater than the set point, the duty cycle must decrease to reach set point power. This is the result of the simulation. The first one shows the system response when the duty cycle is 75.8% like converter design, but the output power exceeds that of the converter design, which should only be up to 900 watts. The second one shows system requires using controls. The set point of FLC are the converter output power. So, if the set point is 800 watt, this percentage of accuracy with setting point 800 watt is 99.559%. The third one shows system response using fuzzy logic control. It using setting point 600 watt. It can be seen that the value of power remains stable at 600 watt. The percentage of accuracy with setting point 600 watt is 99.5%. And the fourth one shows the system response using controls. Setting point used is 400 watt, and it can be seen that FLC can stabilize the power at a value of 400 watt. The percentage of accuracy with set point 400 watt is 99.25%. This picture shows the response of the system using the control when given disturbance to the PV with setting power point of 600 watt. Disturbances are given by decreasing irradiance received by PV. In the beginning, PV was given an irradiance value of 1000 watt per square meters, and then irradiance value was reduced to 700 watt per square meters as the first disturbance in 2.5 seconds. It can be seen in the 2.5 seconds there is the instability of the response occurs in the system. Then in the 4th second it is disturbed by reducing the irradiance to 600 watt per square meters. It can be seen in the 4th second there is the instability of the response in the system. However, after the instability of the response, the power output is stable at the set point. And second pictures shows the response of the system using control when the resistance is varied with setting point 600 watt. Variation of the resistance is given in second 1 to 4. It can be seen that every second when there is a change in the value of the resistance, the results of the system response can still stabilize the power output on the system. This proves that the controls can work well. From the result, it can be concluded that Cock converter simulation results using fuzzy logic control indicate that the system works well. Before the system is controlled, the value of the output power generated are not according to design. When the system is controlled, the system can maintain power in stable conditions with a fairly fast response time. When the system is interrupted, instability occurs in the system for several seconds. However, the control can make the system stable again quickly. The error of this control is 0.25%, and the average level of system accuracy to match the power set point is 99.459%, and the highest accuracy obtained is 99.625%. This error is relatively small with average error is 0.25%, and the level of accuracy of the system is good enough so that the fuzzy logic control used in the converter can work well. This is the end of the presentation, and thank you. Wassalamualaikum warahmatullahi wabarakatuh.